science. The next talk is SOS lower bounds for MCSP, and Kilian will give it.
Yeah, hello. It's joint work with one of my PhD advisors, Per Ostrin, who is not here, but yeah. It's a rather short talk, so feel free to interrupt me and ask questions. I think we have enough time. Okay, so first, so what is the MCSP problem? We have seen it before. Well, you're given a truth table of a function that is computed, a Boolean function that is computed on n bits. And the question is whether there exists a circuit over, say, the basis and or a not of size at most s. Okay? So I'll denote it by MCSP of fs, the question whether there is a size at most s circuit computing the given truth table f. Okay? So it's not so hard to see that MCSP is actually an NP because given a circuit we can check whether it actually computes the supposed truth table. And I mean the big open problem is whether it is NP hard, and we don't know. And furthermore, we even know that if we could prove NP hardness, then we would get circuit lower bounds. So we don't expect this to happen anytime soon. So at least what we could try to do is try to show that certain efficient classes or algorithms, certain efficient classes of algorithms do not solve the MCSP problem efficiently. And this is somehow my excuse to do proof complexity. So let me quickly introduce proof complexity, what this is. We've seen it already yesterday, but just again, it's a study of certificates of unsatisfiability, or also known as proofs of unsatisfiability or refutations. I'll use these terms interchangeably. And the main question to answer or to study is if you're given an unsatisfied Boolean formula, whether this can actually be certified. And now it can always be certified, but very inefficiently by just listing all the truth assignments. But, well, can this be done efficiently? And that's just the question of whether MP is equal to co-MP. So if you want to prove lower bounds, we have to restrict our proofs. We cannot prove this in general because otherwise we would separate NP from co-NP. So we focus on concrete proof systems. And in this talk, we'll focus on the sum of squares proof system. Okay, and we'll show that MCSP lower bounds for the SOS proof system. Good. And yeah, thereby, like, we rule out that algorithms captured by the SOS proof system actually can decide the MCSP problem. Good. So MCSP has been studied before in proof complexity, and so let me just give a quick overview. So first, you have to translate this MCSP problem into a Boolean formula, and you can translate this into a CNF formula over a lot of variables. Just remember, it's like 2 to the n times s many variables. So like the setting of parameters is somehow off from the usual setting. But what the precise formalization is not so important at this point. Just remember, it's many variables. Okay? And it's actually quite central to proof complexity because, like, if we can show refutation lower bounds for a proof system, in particular for the MCSP SAT, for the SAT language, which is 1 if and only if the encoding is actually a satisfiable 3CNF, say, then we kind of show that NP contains this P/poly requires long proofs in this proof system. Okay. And also, like, the other reason to study it is because this is one of the few formulas that are conjectured hard for strong proof systems, and we have somehow few of these formulas. And let me just survey quickly the known lower bounds. So for polynomial calculus, don't worry if you don't know what this is. It's just a proof system. For polynomial calculus over any field, we have degree lower bounds. For resolution, we have actually size lower bounds in a long line of works, like proving these weak pigeonhole principle lower bounds to finally establish these MCSP lower bounds by Ras and Rasparov. Like the last one is Rasparov, the one before is by Ras. And then Rasparov has also shown something slightly stronger, namely that res epsilon times log s also requires superpolynomial size proofs. And in that paper, he also showed size lower bounds for polynomial calculus. But yeah, but it has been open for so far to actually show lower bounds for semi-algebraic proof systems such as SOS, and in particular, it has been open to prove degree s lower bound on the MCSP problem for sum of squares. Okay. Good. So let me quickly introduce what the sum of squares proof system is. So if you're given a system of polynomial equations, P here, where each one of these PIs are our axioms, then an SOS certificate of unsatisfiability is like a list of polynomials T1 through TA and S1 through SP, so that if you multiply the TIs by the axioms, PIs, and sum them, plus you add in the SJs squared, then you get equal to -1, like as a formal polynomial. And this is like a refutation, and it exists even only if P, the system of polynomial equations, is unsatisfying, like doesn't have a common root. Okay, then like just some standard measures. The SOS degree of refuting P is the minimum degree of any SOS refutation, and the SOS size of refuting P is the minimum number of monomials in any SOS refutation of P. Okay? Good. So then we can state our results. So our first result is that for any Boolean function, SOS really requires almost linear degree in S to refute the MCSP problem. So S needs to be at least some large polynomial, and then it holds that SOS requires S to the 1 minus epsilon degree to refute the minimum circuit size problem. And it's, yeah, maybe should point it out that there is indeed the order of S degree upper bound in SOS, where you just like condition on a circuit and then check whether the circuit actually computes your function or your truth table. We also have a result about size, but it's not as general as the first theorem. So here we can only look at truth tables which are like somehow the hardest to refute. Namely, it's truth tables that almost have a circuit of size S, in a sense that they have a circuit of size S that computes out F, like the truth table, on all but T inputs. Okay, so on T inputs, it's wrong, and it has to declare that it's wrong on these T inputs. And if such a circuit exists, then we actually get these exponential in S squared over T size lower bounds for, again, the MCSP problem. And just to get you like a feeling for the parameters, so if we set S to be 2 to the n to the 0.99 and T to S to the 1.5, then we get these double exponential size lower bounds, which we would expect in N. Okay, remember like the setting of parameters is a bit off from the usual setting. So instead of like single exponential, we go into double exponential. Yes? Sorry again? So our theorem only holds for large enough polynomial circuits. So if you ask me about linear sized circuits, then I cannot say anything. But if like the formula encodes a large enough circuit, then I can say something. Okay. Okay. Any other questions? Okay. And we also have like similar results for the monotone setting, but there it only holds for monotone slice functions for the usual reasons, because they're like universal. It's basically just some technical work, and then you get there. I'll show you in a bit what first the theorem, how to prove that. And from there you can go home and do it yourself to adapt it to the monotone setting. Okay? Good. So in the remainder, I'll give you some idea of how to prove the first theorem, the degree lower bound. And then the second theorem follows by standard as degree size trade-off. Okay. So let me first come back to how to encode the MCSP problem. So what is it claiming? It's claiming that there exists a circuit C such that on all inputs, like in 0, 1 to the n, it holds that this circuit actually computes the given truth table. So a way to encode this is to have a CNF formula that is split into two parts. So the first part ensures that these variables y encode a proper circuit. And this second formula then later on claims that this circuit that is encoded by these y variables really evaluates to the truth table. Okay, so this first part of the formula simply states that it's satisfied if and only if the assignment beta to the y variable encodes a valid circuit of size s. And then we have the second part. And it's like this part of the formula is of like size s squared. You can think of it as a local encoding where every gate or supposed gate in your circuit has like some indicators that tells you what the function is that is computed there and how it's connected to the rest. And then we have the second part of the formula, which is over 2 to the n times s many variables, which like simulates an evaluation of the supposed circuit. Okay? And it makes sure that this supposed circuit actually computes your truth table on all assignments alpha. And now the idea of these lower bounds, or how to prove that this MCSP problem is hard, usually goes along the way that it restricts the first part of the formula so that we're left with a nice class of circuits that we need to rule out that it computes the truth table. And in fact, it's going to be so nice, like this class of circuits is going to be so nice that it's equivalent to refuting a known hard formula. And this known hard formula will be the classic hard formula for SOS, which is this K XOR formula over an expander. Okay? Okay, so let me first like explain what this K XOR formula is. So I suppose most have seen this before. So we have, like this formula is defined over a bipartite graph, which is expanding. On one side, we have all the constraints here, D1 through D2 to n. And on the other hand, we have the variables. And every constraint computes the XOR over the incident, the adjacent variables. And then we have a vector f to which it should evaluate to. Like this XOR should evaluate to this value f sub alpha. Okay? And now the problem is, does there actually exist a Boolean assignment to these z variables so that all these constraints are satisfied? Okay? So our task, what we want to do is we want to restrict the first part of the formula, so this circuit sub s of y part, by a restriction rho, so that all remaining assignments to this first part of the formula, all remaining assignments, satisfying assignments gamma, actually encode a nice circuit so that on input alpha, it computes the constraint alpha. It computes the XOR of the neighborhood of alpha on some constants gamma. Okay? So let me try to draw a picture. So we first hit this circuit sub s of y formula by a restriction rho, and we are left with a class or a family of candidate circuits, which we still need to rule out that they could be a satisfying assignment to our formula. And these circuits have like the normal input x, but you also want to think of them as having an input gamma, which is like the remaining assignment to this formula that makes it satisfying. So you can think of every circuit in this formula as having two inputs. It's the x inputs and the gamma inputs. And this uniquely determines the circuit. And furthermore, we want that such a circuit has a very specific form. Namely, we want that on input alpha, it computes the XOR of the neighborhood of alpha over these constants gamma. Okay? And now we want to think of these gamma constants as an assignment to our z variables here. Okay? So in particular, like if alpha is this node here, then it computes now the XOR of these three gamma constants here, or gamma input variables. And if it's like a different vertex, then it computes the XOR of those, or the XOR of these. Okay? And remember that the second part of our formula actually makes sure that this should be equal to f sub alpha. So you should think of this right-hand side, or this constraint vector f, as like the truth table that we're given. Okay? So now this family will have, this family of circuits will actually have like 2 to the m many, will be a size 2 to the m, like one for each assignment to these z variables. And now I hope it's somewhat evident that like refuting that there exists a satisfying assignment over this family is equivalent to refuting that this CSP instance here has a satisfying assignment. And then there are some technicalities, like you need to make sure that this neighborhood relation here can be computed efficiently, and you need to use like some explicit expander constructions. And you appeal to like the known SOS lower bounds to actually obtain the degree lower bound for the MCSP problem. Are there any questions?
Do you end up, when you say use explicit expanders, do you end up choosing a specific F that you prove a lower bound for?
No. It holds for any F. So I mean, certain Fs will actually have a circuit of this form, or just any small circuit, and for those it's satisfying, so then there's nothing to prove, but then for all others we actually get the lower bound. So it really holds for any truth table.
Okay, these expanders that you use are somehow they're like used just inside of the proof.
Yes, inside the reduction, yes. Yes?
What's special about SOS here? It seems like all you're using is that KXORs are hard.
Yes, so we are also using that the lines of the proof, I mean, SOS is strong enough that you can plug in, replace variables by low degree polynomials. So in particular in cutting planes, I cannot do it.
Kind of not obvious where that's
Well,
why wouldn't we sort for like down depth Frege or something?
yeah, well, for bounded depth Frege, we don't have the starting point. We only have Zetin lower bounds, and those don't like, the main issue is again that you need to have more constraint than variables here, and like Zetin lower bounds go the wrong way. You have fewer constraints than variables, so that's the reason why this doesn't work. But it would, like, in principle, this.
The plugging in part would still
Yes. Yeah, so the issue is where you need to replace variables by low degree polynomials is that in here you have many extension variables which you want to get rid of, and to do this you need to like replace them with low degree polynomials. Okay. So yeah, so that's essentially it from my side. Yeah, so just like let me remark that we can use the same ideas to recover the polynomial calculus degree lower bounds. This unifies and also simplifies certain MCSP lower bounds, at least the degree lower bounds or width lower bounds. It highlights these equational CSPs. We should try to prove lower bounds for these over expanders, because then you can use this reduction and we get MCSP lower bounds. And some open problems. One of them is trying to prove cutting planes lower bound for MCSP. I have no idea how to do this. I think it's a really nice open problem. Whether we can prove like more general size lower bounds for SOS, but this again seems difficult because it relates to this problem of proving size lower bound outside the classic degree size relation, so that we seem to be really bad at. And finally, like a question, like can we restrict the circuit classes in a way so that SOS can actually prove something? So why we started studying the monotone setting was that we had some hope that maybe SOS can actually prove something there, but turns out it can't. Is there like any setting of circuits where SOS can actually prove something, or pick your favorite proof system and prove it or something else? Yep, that's it. Thanks.
Right. We have a lot of time for questions.
I am not an expert on MCSP. I'm sorry. I don't know. Yeah, I don't know.
So you have this condition that you need S to be sufficiently large.
Yes.
For these to hold. So do you know for S small, is it easier for SOS to refute? Or do you, like, is there some reason to expect that, or is this just a technical?
No, I think this is just a technical issue because we have to encode this neighborhood function, and we need some size. Like, yeah, it just comes with an overhead, and this is just the reason why we have this condition. I mean, I think it should hold for linear circuits.
So when you're doing the size, you can figure out if you lose this vector.
Yeah. So you will have the number of variables will depend on t. You will substitute and restrict everything else away so that you're left with order of t many variables, and then this comes from the size degree relation that you get this t factor. Yeah.
You might have already said, but where's the 1 minus epsilon?
This comes from the explicit graph, like the expanders. You just incur this loss of this construction. If you can give me better explicit expanders, let me know. Okay, yeah.
More questions? So MCSP has a lot of variations. Are your techniques flexible to, for example, if we have partial MCSP where the truth table is incomplete, we have MCSP against circuit classes of different kinds. We have, these kinds of variants
Yeah.
with multiple outputs, some that are known to be NP-hard.
Yes. We. Yeah, to admit, like we ran kind of out of energy at some point with this project, so we stopped looking at these things. I suspect they're all hard. That's my feeling. Like you don't need much to prove lower ones for it. Yeah.
Can you get anything with like homograph complexity stuff?
I have no idea. I never investigated this. I really don't know. I didn't know.
Right. If we still have time, but maybe we can set up the next speaker. Let's thank the speaker.